Most people ask, why is light the speed limit? But that's the wrong question. It's like asking why water is wet. Water isn't wet. Wetness is what happens when water touches things. Water is just water. Light speed isn't a speed limit imposed on the universe. It's not like a highway with a sign that says 299,000 kilometers per second, do not exceed. The speed of light is the universe itself. Let me show you what Carl Sagan understood about this, what he spent years trying to help people see. It starts with something simple, something you already know. But knowing it and understanding it, those are very different things. Let's start with the moon. You look up at night, you see the moon hanging there, solid, stable, not falling. But here's what Carl Sagan would point out. The moon is falling right now. It's been falling toward Earth for billions of years. Wait, you're thinking, if it's falling, why hasn't it hit us? Because it's also moving sideways. Imagine you're standing on a cliff and you throw a rock horizontally as hard as you can. The rock moves forward, but gravity pulls it down. It curves. Eventually it hits the ground. Now imagine you could throw that rock so fast that by the time gravity pulled it down 16 feet, which is how far things fall in 1 second on Earth, the Earth's surface had curved away beneath it by exactly 16 feet. The rock would never hit the ground. It would just keep falling and missing, forever. That's an orbit. That's what the moon is doing. Now here's where it gets interesting. And this is where Sagan would lean in and make you see the connection. Isaac Newton looked at the moon and did something brilliant. He asked, how much is the moon falling? The moon is 240,000 miles from the center of Earth. We're standing on the surface, 4,000 miles from the center. So the moon is 60 times farther away. Newton thought, what if gravity gets weaker with distance? What if it follows a mathematical rule, an inverse square law? That means if you go twice as far away, gravity becomes 4 times weaker. 3 times as far, 9 times weaker. If that's true, then at the moon's distance, 60 times farther, gravity should be 60 squared times weaker. That's 3,600 times weaker. On Earth, things fall 16 feet in the first second. If gravity at the moon is 3,600 times weaker, then the moon should fall toward Earth by 16 feet divided by 3,600. Do the math. That's about 1/20th of an inch per second squared. Newton calculated it. Then he measured the moon's actual orbit. They matched perfectly. This wasn't just a theory. This was a prediction. Newton connected 2 completely independent facts, how fast things fall on Earth and how far away the moon is, with one law. And that law worked. It predicted the exact motion of the moon. It predicted the orbits of planets. It explained the tides, why the Earth is round, why everything in the solar system moves the way it does. One law connecting everything. But here's what matters for our story. This was the beginning of an avalanche of discoveries that's still going today. And the next piece of that avalanche came from somewhere unexpected. So Newton had his law of gravity. It worked. It predicted things. But then something strange happened with Jupiter's moons. Astronomers were watching Jupiter's moons very carefully, timing their orbits, using Newton's laws to predict exactly when they'd emerge from behind Jupiter. And the predictions were wrong. Sometimes the moons appeared 8 minutes early, sometimes 8 minutes late. 8 minutes? That's not a small error. That's huge. People started to panic. Was Newton wrong? Was the whole law of gravity falling apart? But then someone noticed a pattern. The moons appeared early when Jupiter was close to Earth. They appeared late when Jupiter was far from Earth. That's odd. A man named Ole Romer looked at this and had a wild idea. An idea so strange that most people thought he was crazy. He said, what if light isn't instantaneous? What if light takes time to travel? Think about what that means. When you look at something, you're not seeing it now. You're seeing it as it was in the past. The time it took light to travel from that thing to your eyes. Most people assumed light was instant. You flip a switch, light appears. Instantaneous. But Romer said, when Jupiter is close to Earth, light from its moons reaches us faster. When Jupiter is far away, light takes longer to get here. That's why the timing is off. He calculated how fast light would have to be traveling to create that 8-minute difference, and he got it. The speed of light, about 300,000 kilometers per second. Here's what Carl Sagan would emphasize about this moment. They found the speed of light not by studying light directly, but by trusting Newton's law of gravity. When something didn't match, instead of throwing out the law, they looked deeper. And they found something new, one discovery leading to another, like an avalanche. Each truth revealing the next, that avalanche is still going. And it's about to get much stranger. Once you know light has a speed, you start measuring it, over and over, getting more precise. And you notice something impossible. Light always travels at the same speed, always, no matter who measures it, no matter how fast they're moving. Let me make this concrete, because this is where your brain should break. You're standing still on a platform. You shine a flashlight. You measure the speed of light coming out, 299,792 kilometers per second. Fine, makes sense. Now you get on a train, a very fast train, moving at, let's say, half the speed of light. You shine the flashlight forward in the direction the train is moving. Common sense says the light should now be traveling faster. Speed of light plus speed of the train. Just like if you throw a baseball forward from a moving train, the ball moves faster than if you threw it while standing still. But that's not what happens. You measure the light. It's still moving at exactly 299,792 kilometers per second. You think, maybe I measured wrong. So you make the train go faster, 90% the speed of light. You shine the flashlight forward again, still 299,792 kilometers per second. You get frustrated. You push the train to 99.999% the speed of light. You're barely slower than light itself. You shine the flashlight forward. You measure. Still the same speed. Light doesn't add. It doesn't combine with your speed. It's always the same, no matter how fast you're moving. This should feel impossible. This should feel wrong. Because in everyday life, speeds do add. You're walking on a moving walkway at the airport. You move faster than the walkway. You walk backwards on the walkway. You move slower. But light doesn't do this. Carl Sagan called this the most surprising fact about nature. Not because it's complicated, but because it's so contrary to everything we experience. So the question becomes, why? What is stopping light from adding to your speed? And that's where everything you think you know about space and time falls apart. Albert Einstein looked at this problem and realized something shocking, something so strange that even today, over a century later, people struggle to truly accept it. Time and space are not fixed. They're flexible, they bend, they stretch, they compress. And they do this for one reason, to keep the speed of light constant. Let me say that again because it's the key to everything. The universe bends time and space, literally bends the fabric of reality to make sure light always travels at the same speed for everyone. Here's how it works. When you move faster, time slows down for you. Your clock literally ticks slower. Not because there's something wrong with your clock, but because time itself is moving slower for you, and distances contract. The space in front of you gets compressed, literally shorter. These aren't optical illusions. They're not measurement errors. Time actually slows. Space actually compresses. And the amount they change is exactly, precisely, the right amount to make the speed of light come out the same for everyone. Carl Sagan explained it like this. Imagine you're always moving through space-time at a constant rate. Always. You can't stop. You can't speed up. You're locked at one speed through space-time. But that motion is divided between space and time. If you're sitting completely still in space, all your motion is through time. You're moving into the future at maximum speed, 1 second per second. But when you start moving through space, you have to divert some of that motion away from time. You're now moving through space and time, which means you're moving through time more slowly. The faster you move through space, the slower you move through time. And there's a maximum, a limit. If you could move through space at the speed of light, you would have zero motion left for time. Time would stop for you completely. This is why light doesn't experience time. From a photon's perspective, a particle of light, it's emitted from a star and absorbed by your eye in the same instant. No time passes. The universe is frozen. You can't go faster than light because you can't have less than zero motion through time. That's the wall. That's the limit. That's the prison. Not a rule imposed on the universe, but the structure of the universe itself. Now you might be thinking, this sounds like science fiction. This sounds too strange to be real. And Carl Sagan would say, I know it sounds strange. But here's the beautiful part. We've tested this over and over and over, and it's true. Let me give you 3 examples. 3 ways we've proven this isn't just theory. First, particle accelerators. Scientists take tiny particles, protons, electrons, and accelerate them to incredible speeds. 99.9999% the speed of light. And guess what happens? The closer the particles get to light speed, the harder it becomes to make them go faster. Exactly as Einstein predicted. It's not that the machines aren't strong enough, it's that the particles themselves resist acceleration more and more. Their inertia increases. They become harder to push. And as they approach the speed of light, their inertia approaches infinity. To actually reach the speed of light would require infinite energy, which is impossible. So nothing with mass can ever reach it. Second, GPS satellites. Your phone can tell you exactly where you are on Earth because of satellites orbiting above you. But those satellites are moving fast, and they're in a weaker gravitational field than you are. So time passes differently for them than for you on the ground. If we didn't correct for time dilation, if we didn't account for the fact that time moves at different rates for the satellites and for you, GPS would be off by miles within a single day. But we do correct for it using Einstein's equations. And GPS works perfectly. Every time you check your phone's map, you're proving that time is flexible. Third, cosmic rays. High in the atmosphere, cosmic rays from space smash into air molecules. This creates particles called muons. Muons decay very quickly. They have a half-life of about 2 microseconds. That means in 2 millionths of a second, half of them disappear. From the altitude where they're created to the ground is about 10 kilometers. Even moving at close to the speed of light, muons shouldn't have enough time to reach the ground before they decay. But they do. We detect them all the time. Why? Because they're moving so fast that time slows down for them. From their perspective, they live long enough to reach the ground. From our perspective, they live longer because they're moving fast. Either way, more muons reach the ground than should, exactly as relativity predicts. It's not speculation, it's measured, it's used, it's proven. The speed of light being a limit is as well tested as anything in physics. So let's come back to where we started, the prison. The speed of light as a cage you can't escape. But here's what Carl Sagan understood. What he spent his life trying to show people, it's not a prison, it's a key. The speed of light isn't a limitation imposed on the universe. It's how the universe works. It's the conversion factor between space and time. It's the rate at which cause and effect can propagate. It's the maximum speed at which information can travel. It's the structure of reality itself. And once you understand that, once you really see it, the universe becomes different. You realize that when you look up at the stars, you're not just seeing light, you're seeing the past. Stars that might not even exist anymore. Light that's been traveling for thousands, millions, even billions of years. You're looking back in time. You realize that now doesn't mean the same thing everywhere. Right now on Earth is different from right now on Mars. Time isn't universal, it's local, personal. You realize that space and time aren't separate things. They're woven together into a single fabric, space-time. And that fabric bends, stretches, warps around mass and energy. Gravity isn't a force. It's the curvature of space-time itself. And all of this, all of it, comes from understanding why nothing can exceed the speed of light. Carl Sagan called this the avalanche of discoveries. Newton figured out gravity by watching the moon. That led Romer to discover that light has a speed. That led Einstein to realize that time and space are flexible. That led to understanding that mass and energy are the same thing, E equals mc squared. That led to nuclear energy, to understanding stars, to understanding the Big Bang, to understanding the entire history of the cosmos. One discovery building on the next. Each insight opening doors to more insights. And we're still avalanching, still discovering, still seeing deeper into the nature of reality. The speed of light isn't just a number. It's not just the fastest thing. It's the thing that shows us how everything connects, how space, time, matter, and energy are all part of one unified whole. Sagan said, "We are a way for the cosmos to know itself." And this, understanding the speed of light, understanding why it's the limit, this is part of that knowing. Not comfort, not simplicity, truth. Strange, beautiful, testable truth. And that's what makes it remarkable.